Hi, my name's Dan, and this video is one of the series that I'm doing on some of the basics of logic circuits in digital electronics. And in this one, I'm going to look at a thing called Karnaugh Maps, which is a way of reducing the logic from that you might have derived from a truth table and bringing down the number of terms. It's an alternative to using Boolean algebra to reduce the terms. And uh, although the concept is a little hard to get hold of to start off with, once you're used to it, and if you can follow the rules, it's actually easier to use than Boolean algebra because it is just a deterministic set of rules. Um, so in order to understand this, you're going to need to have some understanding of logic gates and logic circuits. You're going to have to understand what a truth table is and maybe a little bit of understanding of Boolean algebra as well. Um, and if any of those things are opaque to you, then go look at some of my other videos in this set. Okay, so we're looking at an example, which is an example that's come through from the previous two videos in this short series, which is that we want to create a circuit which takes a digital input, which is going to be a decimal number 10 or decimal number 11, but we're going to convert that into binary. And in either of those cases, we want to have a 1 high at the output, and in any other case, we don't want to have that. So we translate that to binary 1010 or 1011. And in two videos ago, I showed how to do that using a truth table. In the last video, I showed how to reduce that using Boolean algebra. And in this, I'm going to show this principle, this process called Karnaugh Maps. Again, the pronunciation of that, I'm still trying to get used to it. Karnaugh, which is gnaw like the Nor gate. Okay, right, so that's what I'm going to use, but what are they? What is this process? Right. Effectively, it's a visual way of reducing a truth table. And you start by going from the truth table to to a different kind of representation of the same thing, which is the K-map or the Karnaugh map. So it is just a different way of displaying exactly the same information. It's just ordering it differently in a different kind of table. So here's a truth table. I've not actually filled in any values here. We've got 4 inputs, and it's fairly traditional to have the A, B, C, D, and for it to be done in binary order, so that you can read the outputs. And we're going to translate from this kind of truth table to the Karnaugh map, which looks like this. Okay. And so what this does is, instead of having separate columns for A, B, C, and D, is that it uses the two sides of the table. One side is going to be going for the columns is going to be the AB values, and the vertical set is the CD values. And as you can see here, for AB, you've got 4 different values that you might have, and so CD, you've got 4 different values. And we're going to put the Z, which is effectively the result, inside this table. So it's AB versus CD. There are a few things to note. They could be the other way around. It doesn't matter which is vertical, which is horizontal. And in fact, it could be any 2 inputs versus any 2 inputs. So we could have done AD versus BC, or we could have done DB versus AC. As long as you've got 2 inputs on one side and 2 inputs on the other side, the order isn't important. But for the sake of your sanity, you probably want to do this in such a way that it's easy to convert from the truth table to the K-map. Also, note the odd order that they're in. Both the AB and the CD are in this strange order where instead of going 0001 1011, it goes 0001 1110. Now, the point of this is that only 1 digit changes between each adjacent cell. And this is an ordering that's called grey code. And if you don't do this, then the process that I'm about to outline doesn't work. So you've got to do this strange ordering to make the K-map process work. So here's a whole lot of values. And in fact, what I've done is I've looked all this up on Wikipedia, and I have used the example that they've used. I've done my own diagrams, so I've not lifted anything from there, but it was quite a good example that they've got. So we've got these values of Z in our truth table, and we've got roughly half of them, in fact exactly half of them, zeros, and half of them are ones, and it converts to the K map on the right hand side. So let's just pick a few and talk through them. So the top row in the truth table is 0, 0, 0, 0. So this is equivalent. The equivalent space on the K map is the top left, which is where AB is 0, 0, and where CD is 0, 0. And so the value we're putting in is 0. Let's also do the bottom right. So the bottom right in the K map, we're going backwards from here, is 1, 0 is the right hand end for AB, and 1, 0 for CD is the bottom. So the ABCD is 1, 0, 1, 0. And if we look in the truth table at 1, 0, 1, 0, we're scanning down over the 10th row, our Z value is 1. So that's the value that we put in the K map. And you will see that there are, in the truth table, there are 16 Z values. And in the K map, there are also 16 Z values. And we represent each of the binary numbers A, B, C, D in the K map in the same way as we do in the truth table. It is exactly the same information. It's just been ordered in a different way, which allows us to do this process. Okay, so let's have a look at the K map and move on with this process. And what are we going to do now? Which is we're going to find regions. So a region is a block of ones that are together. So there are several rules that we need to apply when we're finding regions. In fact, there are 4 of them. Here we go. So the first one is the region must be a rectangle. It can't be kind of an L shape or anything like that. We can only use rectangles for regions. The second one is it must have 2, 4, or 8, or, well, a multiple of 2 cells. It would be pointless using any that were 1 cell only, because this gives us no reduction. It's the size of the cell that gives us so the size of the regions that gives us the reduction. And the larger the better in that sense. And then the final rule, no, 2 more rules. First, next rule, you can overlap. So you can have 2 regions that share cells. And this is very useful, as you'll see, as we keep going through this example. And the final rule is they can wrap around the edges. So this is partly why we've got this strange ordering, is that if you see from left to right on AB, we've got 0, 0, 0, 1, 1, 1, 1, 0. But if you kept going and you wrapped round, you'd get back to the 0, 0. And that's still only 1 digit change in your AB from 1, 0 to 0, 0. So if you really want to think about the topography of this, it's shaped like a torus, but I don't want that to confuse you too much. Most people these days have played video games or something in which you have maps where you get wraparound, you wrap around the edges, and you're just able to think of this as wraparound. Actually, in the examples that I'm going to do, this example and the example 3, which is our 10 and 11 numbers, neither of those actually use wraparound. So that rule, I need to tell you the rule, but we're not actually going to use it. We are going to use the overlap rule, we're going to use the other rules as well. So we're going to find the regions that do this, and what we want is to find a set of regions which will cover all the ones in our K-map. So here's one region, we've got a pink region here. Here's another region, which is green, which gives us a full column here. Here's another region, which covers just a couple of ones in the middle, and if we combine all them together, we can see that between all these 3 regions we're covering the ones. The orange region and the green region are overlapping, and that's allowed within our rules. In fact, that's part of the power of K-maps, is to use these overlaps. So between these 3 regions, we're covering all the ones. Right, what next? So for each region, we need to find out what is the Boolean term that represents that region. So we're going to do this by seeing which of the the four elements, the A, B, C, D bits, change inside the region, and those are the bits that we're going to ignore. And then we're going to find the bits that don't change, which are fixed, and we're going to express them as, say, for example, C and not D, and whichever particular values that we've got. Okay, so let's do each one in turn. Let's take the orange region. So for this region, the four numbers that are covered, the four binary numbers, are, and I'm going to go from left to right, top to bottom. So it's 1100 is the top right, top left. 1000 is the top right. 1101 is the bottom left, and 1001 is the bottom right. That's the binary numbers A, B, C, D, and we can see that inside this orange box that the B element changes. So between the two columns, the 1 1 and 1 0. So the B element can be 1 or it can be 0. So it doesn't matter for this region. And similarly, the D changes as we go between the top row and the bottom row of the orange region. The D, which is represented on the rows, changes from 0 to 1. So the B changes and the D changes. They're the things that we're going to ignore, and we're going to see which ones are fixed. A is fixed, so for the whole of this region, A is 1, and for the whole of this region, C is 0. If you haven't got that and you need to spend a little bit of time looking at that and checking it, then just pause the video and look at this text that I've got and have a check that you realise that this is the case. The Boolean term that represents this region is A and not C. Right, let's have a look at the next one. So for this region, I'm going to go slightly faster. C changes and D changes. This is fairly obvious with it being a vertical column that neither C nor D has an effect on the fact that there is the number is inside this region, and it's only A and B that have an effect. And in fact, it's because it's the 1 0, it's A and not B. Okay, so that's the Boolean expression for this region. And then we got a third region, which is a smaller region. So the only thing that changes in this region is A. So as you see on the columns, we've got the column 0, 1 and the column 1, 1. So A changes, but B doesn't. B stays the same. So the things that are fixed are B and C and D, and they're all ones. So we want B and C and D. And that's the Boolean expression for this region. So what we're going to do is we're going to combine these three regions to get our final Boolean expression for the output. So we've got A and not C, and we've got A and not B, and we've got B and C and D, and that represents three regions. And what we need to do to put them together is to just take those three terms and put them in alls. Okay, so it's a bit like doing the truth table as a whole, where you take every line that gives you a 1 output, and you get the Boolean expression for that line, except instead of doing individual lines, we're doing it in regions, so it reduces the complexity of it. And that is probably, as far as we can reduce, it's certainly a reasonable reduction of this particular example. Okay, so that's just kind of stretching onto one line. Okay, so some principles I want to quickly throw at you before we go back to our more basic example, the numbers 10 and 11. The one is that you want as few regions as possible, and that's fairly obvious because the fewer regions you have, the fewer terms you have in your final equation. The second one is you want as large regions as possible, and again that should be fairly obvious because, as you saw with the regions that we did, the larger regions had smaller Boolean expressions. Okay, so in terms of reduction, you want to kind of get this balance between as few regions as possible and as large regions as possible, and don't worry about how much overlap you've got, because that is really where the power of the K-map comes in, is being able to allow these overlaps. There's a couple of other things. We can do fewer or more than 4 inputs. We've just done an example that's 4 inputs. If you're doing 5 or 6 inputs, the K-map becomes more complicated, and you're making sure you get the right order of the things with your grey code ordering. You need to make sure you do that, but just follow the rules. And you can do fewer. So a 3 input will instead of being a 4x4 grid for your K-map, will be a 4x2 grid or a 2x4 grid. And for 2 inputs, you've just got a 2x2 grid. By the time you get down to 2 inputs, actually the process of doing a K-map is you can usually do it by inspection anyway, by being able to look at it. And the final one is it's also possible to do this using the zeros instead of the ones. And so sometimes you have a solution where the regions that you get work better for the zeros than they do for the ones. So once again, you just go through the same process with the zeros, except at the end, instead of combining them with or, you combine them with basically with a NOR gate. You want the situation where none of the regions is actually true, and so you can guarantee that your output is the right output from that. Right, so let's apply this to. We've done a whole lot of principles. We've done a more complicated example, actually, than the example that we wanted to tackle, which is we've got a decimal input of 10 or 11, which is a binary 1010 or 1011. So, truth table. And we've got the, if you look on the Z column on the right hand side, we've just got those 2 elements that have got the ones in them. And we're going to convert that into a K-map table. Which looks like this, and in fact, so once again, we've just got those 2 outputs that give us 1 on the far side. And we're going to inspect this, and we're going to find the regions. Oh, look, there's 1 region. It's really not very complicated at all. So D changes between the 2 regions. We can ignore the D element, therefore, and in fact, this gives us A and not B and C. Now I'm just going to flick back to DigitalWorks, which is still set up from the previous video, which is when we did algebraic reduction. And in fact, we can see that when we did our algebraic reduction, we got exactly the same term, which is A and not B and C. And so our circuit would come out in exactly the same way. So I don't know which of these processes you would personally find easier. The K-map for this example is really simple because it's just the one little region. And in fact, as I indicated at the end of the last video, actually, with this particular example, you can kind of see in the truth table as well. You can see that the D changes and you've got these 3 values that are the same. So you can infer the same information about that is effectively a region there between those 2 values out. Anyway, so that's probably the end of this short series about principles of logic, logic circuits. I've shown you how to how to think about going from a problem to a circuit, how to use a truth table to produce a circuit, how to reduce the terms that you've got and therefore the gates that you need using algebraic reduction, and that was the previous video. And in this one, I've done Karnaugh reduction using a Karnaugh map. And from here on, this this kind of big set of videos is going to start working towards the idea of how can you go about using these gates to produce a computer. But that's it from me for now.